Today's lesson is called Series and Convergence. So we're going to start with a concept that you talked about in pre-cal, a geometric series. Please excuse my handwriting. It's hard to write with a stylus as opposed to a pen or pencil. A geometric series is one in which each term is obtained by multiplying the preceding term by a constant ratio r. The initial term is a. So an example of a geometric series that you ought to be quite familiar with is your repeating decimal 0.33333, which can be represented as 3/10 plus 0.03, which is 3/100, plus 0.003, which is 3/1000, plus 0.0003, which is 3/10,000, plus ... The pattern continues. So this repeating decimal is represented by the series where n starts at 0 and goes to infinity of the first term, which would be 0.3 or 3/10, times the common ratio, which is what we multiply by to get from one term to the next each time, 1/10 raised to the nth power. And that is from the general form, the sum from n equals 0 to infinity of a times r raised to the n power. And you had a formula that you learned in pre-cal to get the sum of that series. A, your first term, divided by 1 minus r, your common ratio. That works if the absolute value of r is less than 1. So a fraction between 0 and 1 is what we're looking at, basically. So the sum of this series would be your first term, which is 3/10, divided by 1 minus the common ratio of 1/10, which equals 3/10 on the top, divided by 1 take away 1/10 is like 10/10, take away 1/10, so that'd be 9/10. And you can multiply by the reciprocal. 3/10 times 10 over 9 equals 3/9, which simplifies to 1/3. And you already recognize that decimal as being 1/3, but this shows you how it all connects together. Now, something else you should know about a geometric series is that if the absolute value of r is greater than 1, like say you're multiplying by 2 each time or something like that, the series, if I could write it in this tiny spot, the series diverges which means there is no sum. It's just going to get to be a greater and greater quantity. It's not going to come out to a specific value if you were to total up all the terms of the series. Okay, so that was some introductory information about geometric series. Let's do a few examples about geometric series. All right, so example 1. We're going to find, oh, sorry for the sloppy writing, the rational number represented by the repeating decimal 0.784, 784, 784, ... So you can think of this as the first term being 784, and then plus the second term of 0.000784, and the third term as being 0.000000784, plus, and so on and so forth. So A is the first term, 0.784, and R, what we're going to be multiplying to get from one term to the next, the common ratio, is 0.001, which is the same thing as the fraction 1 over 1,000, 1/1000th. So to come up with the rational number, we're going to use that formula that you learned in pre-calc, A divided by 1 minus R, for the sum of the series. So this is equal to the first term, 784 on top, 0.784, sorry, divided by 1 minus the common ratio of 0.001. So that's going to be 0.784 divided by 0.999. And we don't normally consider numbers to be simplified when we have decimals inside of fractions, so I'm going to multiply, hang on, where's the erase button? There we go. Multiply this times 1,000 over 1,000, which is a clever form of the number 1, and the reason I'm doing that is to move the decimal 3 places to the right on top and the bottom. So that's 784 over 999, which is the rational number that repeating decimal can be represented as. Okay, let's look at example 2. We are going to, in this example and the next several, determine whether the series converges, which means it has an actual sum that all the terms add up to, and if so, find its sum. So, example 2 is the sum from k equals 0 to infinity of 5 over 4 to the k power. So, another way to write this is the sum as k equals 0 to infinity of the first term 5, pulling that 5 out in front, times 1/4 to the k power. So that's algebraically equivalent to what we started with, and the reason I changed it to look like this is because it works a little bit better with our a times r to the k power form of the series to recognize the a value and the r value. So we can see here a is 5, that's our first term, and r is equal to 1/4. If you're ever not sure, you can always just substitute 0 in for k for your first term, substitute 1 in for k for your next term, and just keep going and generate a few terms of the series to see what those values are coming out to each time. So I'm going to say, yes, this series converges, and the reason why is because the absolute value of r is less than 1. 1/4 is less than 1. And now find the sum. We use the a over 1 minus r formula. So 5 is the first term divided by 1 minus 1/4. So that's 5 divided by 3/4. So that's 5 times 4/3, which is 20/3. So the sum of all of the infinite terms in that series comes out to 20/3. All right, number 3. We're going to do the sum from n equals 0 to infinity of 1/5 times 11/10 raised to the nth power. So does this series converge? If I was there with you, I'd wait for you to answer. And you got it. It diverges. It does not converge. It does not have a sum. And the reason is because the absolute value of r is greater than 1. All right, number 4. And just FYI, feel free to pause the video at any time if I'm going faster than you need me to, because I'm not there with you to have you raise your hand and say, I need a little bit more time. Number 4, we're going to look at the sum from k equals 1 to infinity of 3 to the power of 2k times 5 to the power of 1 minus k. And that looks kind of crazy. That does not look like our normal format. So sometimes they give you a geometric series that's kind of disguised, and you have to use some sneaky algebra, not really, just some basic algebra manipulation to get it into that form. Okay, so let's try that. The sum from k equals 1 to infinity. First of all, I know 3 squared is 9, so I can go 9 to the k. And then I don't like that negative k power, so I'm going to change this to 5 to the negative 1 pulled out of positive k minus 1, because if I distributed that negative back in there, I'd have my negative k and my positive 1. And now I'm going to scoot that down to the denominator so I can get rid of that negative power altogether and say 5 to the k minus 1 on the denominator. And my next step, that's a minus, sorry. I would really like to have a minus 1 on the k so that they, on the k on the top so that they match. So I'm going to force that to happen because I know that if I have the same base and I add my powers, that it should come out equal. So if I want 9 to the k minus 1, I could just multiply it by a 9 to the just 1, just a 1, because minus 1 then plus 1, that is equal to what I had before of 9 to the k, over 5 to the k minus 1. And so now, pardon me, these k minus 1 things, they have the same power, so I could put them together, and I could rewrite this as the sum from k equals 1 to infinity of 9 multiplied by 9/5 raised to the k minus 1 power. So what does that mean? Well, my r is 9/5. That's what I'm multiplying from term to term, which is a number greater than 1. Therefore, the series diverges. Okay, we only have one more example for geometric series. Number 5. The sum from k equals 0 to infinity of x to the k can be written in expanded form by putting the 0 in for k. So k to the 0 would be 1, and then, x to the 0, sorry. X to the first plus x squared plus x cubed, and so on and so forth, plus x to the k plus dot dot dot. So we can see that the first term is 1 and the common ratio is x. So does this series converge or diverge? Well, it converges when the absolute value of x is less than 1, and it diverges when the absolute value of x is greater than 1. So the sum, if the absolute value of x is less than 1, would be equal to from k equals 0 to infinity of x to the k would be equal to the first term, which is 1, divided by 1 minus r. So that's the sum of the terms of that series. Okay, next we're going to talk about a telescoping series, which is a different kind. You've done geometric series, a little bit of work with them before in pre-cal. Telescoping, this will be the first time you've seen these. In order to solve telescoping series, to find their sums and determine if they converge or diverge, you're going to use partial fractions. So this is example 6. The sum from k equals 1 to infinity of 3 over k squared plus 3k plus 2. Oops. Sorry. Okay. So the first thing I want to do is take that 3 that's on top and pull it out in front. So we're going to have 1 over k squared plus 3k plus 2. Now, you can recognize a telescoping series, or that a series might be telescoping, by noticing that it would have a constant on top, like this one had 3. You can always move that constant out in front to make it 1. And that your denominator would be a quadratic that is factorable. So let's factor that. 1 over k plus 1 times k plus 2 would be a over k plus 1 plus b over k plus 2. And we're going to solve for a and b. So multiply by the denominator on both sides. 1 equals a times k plus 2 plus b times k plus 1. So 1 equals ak plus 2a plus bk plus b. And we'll regroup our k terms together and the constant terms, and we'll go ahead and factor at the same time. So a plus b times k plus 2a plus b times 1 for the constant term. So solving this system, we have a plus b has to equal 0 because there is no k term on the opposite side, and 2a plus b has to equal 1. So if I multiply the first equation by -1 and add it to the second equation, I get a equals 1, And if a is 1, 1 plus b has to equal 0 from the first equation. Subtract the 1 from both sides. B equals negative 1. Okay, we're going to move to the next screen now. So I'm rewriting 3 times the sum of k equals 1 to infinity of 1 over k squared plus 3k plus 2 as 3 times the sum of k equals 1 to infinity of 1 for my a value over k plus 1 plus b negative 1 over k plus 2. Now, that would be 3 times. I'm going to generate out some terms here. The first term, if I plug 1's in for the k's, is going to be 1 over 1 plus 1, so that's 1/2, minus 1 over 1 plus 2, which is 3. So that's using both of these terms to make these. Next, the second term would be plugging 2 in for the k's. 1 over 2 plus 1 is 1/3, minus 1 over 2 plus 2 is 1/4. Now we're going to plug in 3's. Positive 1 over 3 plus 1 is 4. Negative 1 over 3 plus 2 is 5. Now, what you'll see happening is the second term of the first, these two were together as the first two terms, but its second part is the same as the first part on the next term, and this continues to happen. Does it continue forever? Well, if I keep going, I'm going to have 1 over k plus 1 minus 1 over k plus 2 is how I'll end as k approaches infinity. And this 1 over k plus 1 will cancel with the term that preceded it, because the second term from that one that preceded it will be the same. But this last one doesn't have anything to mark out with. So what we do is we look at the limit as k approaches infinity of 3 times that first term 1/2, because it didn't cancel with anything. The 1/3's canceled, the 1/4's canceled, 1/5 will cancel, this one cancels with the one that comes before it, but the 1/2 and the negative 1 over k plus 2 as k goes to infinity are still going to be around, so minus 1 over k plus 2. But the limit as k goes to infinity of this, if that denominator gets huge, this is just going to 0. So this turns out to be 3 times 1/2 minus nothing. So the sum is 3/2. So yes, it converges, and the sum is 3/2. All right, so let's look at another one of these. Number 7. The sum from n equals 1 to infinity of 1 over 2n plus 1 times 2n plus 3. So the first thing I want to do is separate it into partial fractions. So 1 over 2n plus 1 times 2n plus 3 is a over 2n plus 1 plus b over 2n plus 3. So multiply by the denominator on both sides. 1 equals a times 2n plus 3 plus b times 2n plus 1. And then distribute 2an plus 3a plus 2bn plus b. And then factor the ends, out of the two terms that have ends, 2a plus 2b times n plus 3a plus b times 1. And now set up my system. So 2a plus 2b would equal 0, and 3a plus b would have to equal 1, which means, well, we can solve this by a couple of different methods. I could do elimination if I wanted to multiply this second equation by negative 2b. This would be negative 6a minus 2b equals negative 2, and then take that over here and add it to the first one. So 2a minus 6a would be negative 4a equals negative 2. Divide by negative 4 on both sides. A equals positive 1/2. And then we could substitute that in to this equation, second equation, to solve for b. 3 times 1/2 plus b equals 1. So b equals 1 minus 3/2. So b equals negative 1/2. Okay, so moving on to the next screen. The sum from n equals 1 to infinity of 1 over 2n plus 1 times 2n plus 3 is equal to the sum from n equals 1 to infinity of a, which we got 1/2 for a, over 2n plus 1, plus b, which is negative 1/2, over 2n plus 3. Now, in sums, you can pull out a constant just like you can in integrals. So 1/2 can come out in front. And then I'd have 1 over 2n plus 1 minus 1 over 2n plus 3. So let's generate out a few terms to see what this equals. If I plug in ones, 1 over 2 plus 1 would be 3. Then minus 1 over 2 plus 3 is 5. Now go plug in 2's. 1 over 4 plus 1 is 5, minus 1 over 2 times 2 is 4, plus 3 is 7. Do you see the pattern coming? Now we're going to do it again with 3's. 1 over 6 plus 1 is 7, minus 1 over 6 plus 3 is 9. And this continues until you get to the quote-unquote last term. There's not really a last term because they keep going to infinity. 2n plus 1 minus 1 over 2n plus 3. So the 1/5 cancel, the 1/7 cancel, the 1/9 will cancel, and the last set, the first term from the last pair will cancel out with the second term from the one that precedes it. So the result is 1/2 times 1/3 minus 1 over 2n plus 3, but this would be the limit as n goes to infinity of this. So as n goes to infinity, that second fraction approaches 0. So 1/2 times 1/3 minus 0. So that's going to equal 1/6. That is the sum of all the terms in that series, and it does converge. Okay, so we've done geometric series and we've done telescoping series. Now we're going to look at another way to determine if series converge or not, and it's called the nth term test for divergence. That's what your book calls it. My old book called it, so also known as the Divergence Test, which I like that name better. So you'll probably hear me refer to it more often like that. Both would be equally understood by AP readers or college mathematics professors. So here's the nth term test for divergence, or the divergence test. If the limit as n approaches infinity of some function rule for a series, so a sub n is just going to represent a function rule that we could put on a series. If the limit of that function does not equal 0, then that means that the sum from n equals 1 to infinity of that function, whatever it is, diverges. So if anything other than 0, you're guaranteed that that series diverges if the limit is not equal to 0. If the limit as n approaches infinity of that same function rule does equal 0, then the series either converges or diverges. We don't know, so the test is inconclusive. So on these problems, they'll say, determine whether the series converges or diverges if possible. Because if the limit is not equal to 0, then we're going to be able to say, yes, it's diverging. But if the limit does equal 0, then we can't say converges or diverges, neither one. You cannot use the divergence test to determine that a series converges. It's impossible. It's either it diverges or we don't know. So let's try one of these. Number 8. Oops. Here we go. The sum from n equals 1 to infinity of n over e to the n. So we're going to use the limit as n approaches infinity of n over e to the n. If I plug infinities there, I get infinity divided by infinity. That is an indeterminate form. When I get an indeterminate form, I use L'Hopital's rule. Haven't seen that one in a while. So that means I'm going to take the derivative of the top and the bottom and look at the limit as n approaches infinity of that. So the derivative of n is 1, and the derivative of e to the n is e to the n. So if I look at the limit as that n goes to infinity, I'm going to get the denominator to be huge. 1 over that huge infinite value is 0. Therefore, the limit equaled 0. The series either converges or diverges by the divergence test. So we're still not sure. Now the next one, number 9, we're going to do the sum as n approaches, as n from n equals 1 to infinity of the natural log of n. So we're going to evaluate the limit as n approaches infinity of the natural log of n? Well, the natural log of infinity equals infinity. Infinity is not the same thing as 0. Therefore, the series diverges by the divergence test. Okay. Next, number 10. The sum from n equals 1 to infinity of 3n over 3n plus 1. So if I take the limit as n approaches infinity of 3n over 3n plus 1, that's going to equal infinity over infinity. So I'm going to use L'Hopital's rule. Take the derivative of the top, that's 3. Take the derivative of the bottom, that's also 3. 3 divided by 3 is 1. So the limit equals 1. So that means it's not equal to 0. And that means by the divergence test, this series diverges. Okay, so we've talked about the geometric series test, the telescoping series, the divergence test, and now we're going to look at the last one, which is the harmonic series. The harmonic series is the series from n equals 1 to infinity of 1 over n. It's always 1 over n. It's equal to, if you were to generate out the first few terms, 1 divided by 1, which is 1, plus 1 divided by 2, which is 1/2, plus 1/3, plus 1/4, plus 1/5, plus dot, dot, dot. So, if you whenever we're dealing with the harmonic series, it's this series exactly. And it's a very special series used in a lot of interesting applications in the real world. This series diverges, but I don't want you to just take my word for that. I'm going to leave a link for proof that this series diverges. And it's a pretty interesting proof I'd like you to watch. I'm never going to ask you to prove it yourselves, but you're at the point in mathematics where it's important to understand that you don't just accept everything because somebody tells it to you, that it can be proven, just like you used to do proofs in geometry and again in pre-cal, to ensure that something is true. I'm also going to leave 2 other links for y'all to watch that are videos that show some more information about the harmonic series. This is a very special series in the real world, and I would like you to have an appreciation of it as you move forward. So, one other thing before you stop and watch the harmonic series 3 videos that I'm leaving about it, I would like you to know how to calculator. So, pause and get a calculator if you haven't got one already. And for example 11, you're going to use your calculator to find the sum of the series from n equals 0 to 100. So this one doesn't go to infinity, it goes to a finite number of 100, of negative 1/5 to the n. Now this is a geometric series, so you could use the formula to find the sum quite easily, but I just want to make sure that you know how to use your calculator to do this. So you're going to, in your calculator, hit alpha and then the window button. This is where we found derivative and integration options, but if you hit option 2, you'll see the sigma, which is the Greek letter, which represents a sum. So you're going to hit 2, and then you can type in, you'll see this window pop up with blank equals blank, with a blank on top, in parentheses a big square. So you're going to do x equals 0, and then go to the top and put 100, then right arrow over in the parentheses. You're going to add another set of parentheses and type -1/5, close that parentheses, and then hit the little caret button to get x in the power, and then press enter, and that equals 0.833, repeating. If you hit math 1 for math fraction, and then enter, it will give you the answer as a simplified fraction, which is 5/6, which is the sum of that series. So, just wanted to make sure that you remembered or knew how to do those in your calculator. Okay, all that's left to do is watch those 3 videos. I hope you enjoy them. I would enjoy watching them with you, but since I'm not there with you, have fun. And your homework is posted. Bye!